One resource for Quest A Plus. One resource. Really? It's supposed to be up there. One resource for you is Quest A Plus, which you may have used. So I'm just going to type it in here because we'll let Google find it. There it is, Quest A Plus, right? So the easiest way to get there, type Quest A Plus. Quest A Plus. .alberta.ca has practice tests. And it has practice tests in, actually for different subjects, right? What you want, grade 12. And they have practice tests in Applied Math 30. No. Biologie 30. Yeah, if you're doing it in French. Biology 30, if you're doing it in English. Chem 30. Really? Is that chemistry in French? Math 30-1, stay away from that. Math 30-2, this is the one you want, right? And you may also want Biology 30, and Chem 30, and Physics 30, and Social Studies 30 whatever. Anyways, let's not go to the French one. So they have a year-end practice, right? Now this is something you may want to do on Friday, all right? And over the weekend. And so you just, click on year-end practice and say, take the practice test. That's something you may want to do this on Friday and Saturday and Sunday because it might take that while. But it's for all diplomas, right? You got practice tests that are available. And so they give you a little formula sheet up here, and I think you can probably scroll that independently. Okay, and then they give you questions down here, which you can scroll independently. And look, starts with a probability, right? Or, yeah, probably. So contestant in a game must draw a single cube from a bag containing 7 red cubes, 4 blue cubes, and 2 white cubes. The odds in favor of the contestant drawing a white cube are, and you figure that out, and then you answer it. And then here's what the test looks like. Okay? Now, I'm not really sure how this works as to whether you can save it or not. So what I would do is I think you're going to get the same test every time. Just write your answers down. So if you do, if you're trying it on Friday and you don't finish it, you want to finish it on the weekend, then you can go in and just enter those answers again. Okay? Or maybe different ones if it told you those are wrong. But anyway, so Quest A Plus, you can copy down the address or just type Quest A Plus into Google and it will get you there. Okay, so that's probably something you should consider doing on Friday. / Saturday, Sunday, and before the field test anyways, right? So before the field test. Go through that. And that first question, right, you're going to get a lot of those. So the test on, Thursday is all multiple choice. Okay? It is, I think, about 27 multiple choice questions, which will, pay attention, which will start at question 21. And the reason it will do that is so we can use the front side of our scantrons again, right? So we get 3 uses out of them instead of reusing new scantrons every time. So all you do, it's number 21, just start at question 21. Okay, the key thing that goes in will only mark through 21 on. Okay, and then there's 27 questions. So it'd be 21 to 47 or something like that. Okay, so all multiple choice, no numerical response, just straight multiple choice. Now you got to read carefully, okay? Because you get questions that says the odds. Is it the odds in favor or is it the odds against? Right. So that's what you need to be asking yourself: odds in favor, odds, because guarantee you the odds against will be one of the answers, right? And then the odds in favor, and vice versa. If it's the odds against, then one of the answers will be the odds in favor. So make sure you know how to do odds. Remember, odds are different than probability. Odds is favorable to unfavorable or unfavorable to favorable. Whereas probability is favorable over total. And to convert an odds to a probability, you have to add together those two numbers because that'll give you the total and then figure out the favorable. Okay. And if it was odds against, you're actually going to have unfavorable, and then you got to work your way through that. Just very important on any of this stuff, and it's all lumped under probability as far as Alberta Ed. That's not for us. It's all lumped under probability as far as Alberta Ed is concerned. That'll be all of the counting, all of the set theory. So there's going to be some counting in there, right? It's going to be some set theory stuff. There'll be some counting in there. You're going to see combinatorics, right? Like, 52 choose 5. You'll see permutations, because that's all part of probability. Probability can be worked out using counting methods. What's the probability of getting a 2 pair or whatever, right? So it's 13 choose 1, 13 choose 2, 4 choose 2, 4 choose 2, 44 choose. They'll never ask you something like that on the diploma, right? But, that's a possibility that it's in that notation, in combinatorics notation. So just be aware of that. And according to a student who took it last semester, he said it's pretty heavy on the probability stuff. It's going to be fairly light on the sinusoidal. Okay? Like there might be 4 or 5 questions on sinusoidal, but they fall into a pretty narrow range, right? Like what's the amplitude, blah blah blah. But heavy on the probability, set theory, counting, etc. Right? Use the Quest A Plus as kind of a guide. Like, just if you as you're doing it, maybe write down all the different units and just put a little check mark and say, okay, there was like one of these, and so how did that test come out? It's like, wow, there was a lot of probability on there, or set theory, counting, not so much in other stuff. Okay, anyways, independent events. What does independent mean? It's what your parents want you to become eventually, probably sooner rather than later. They want you to be independent. So if you're independent, what does that mean? Yeah, you're out of the house, right? You're living on your own. You're independent. You're not depending on anybody. That's what independent. In a probability sense, independent events are events that have no effect on each other. Right? So the probability of event A does not affect the probability of event B. So an example of independent events would be like tossing a coin. Whatever I get on the first toss, does that affect the second toss? No. Right? Because basically, we're back at the same starting condition, right? I got a coin. Okay, so independent events. I was going to say define. Events are independent. If the outcome of one event, let's say event A, has no effect on the outcome of event B. So we can say either A and B are 2 totally different things. Use the technical term things like rolling a die. So 2 totally different things, right? Rolling a die and tossing a coin. Oh, and by the way, independent is with the word and, right? This is still an and probability. So rolling a die and tossing a coin. Drawing a card. And tossing a coin. What else is independent? No, you got the idea, right? I mean, how many more things? So you're doing 2 totally separate things. So there's no way that rolling the die could have any effect upon me tossing a coin, right? They have nothing to do with each other. There's no way that rolling a die would have an effect on, I rolled a 6. Oh, that means that the card that I'm going to draw depends on, no, right? Because they're 2 totally separate things. So if A and B are 2 totally separate events, then the first thing you think is, these are independent, right? And I'm going to use the formula for independent events, which we'll get to in a half sec. Or If you're doing the same thing, then you will see, so if A and B involve the same thing, you will see the words with replacement. Or something to that effect, right? Like put back. But in effect comes down to with replacement. With dependent events, you see the words without replacement. And dependent events have to be kind of the same thing, right? You can't, because otherwise they'd be independent events if it was different stuff. So dependent events are always say, oh, I'm drawing a card and then I'm drawing another card. Now, okay, is that dependent or independent? Well, let me keep reading. Draw a card and then I draw another card without replacement. That's dependent, right? Because it's going to change the number of cards in the deck, right? In other words, with replacement means you're back to the original starting conditions. Okay? See, there was with replacement, so you will be back at the original starting conditions. Okay? So I draw a card, and I look at it, and then I put it back. When I go to draw the second card, I'm back at the original condition, right? I have a full deck of 52 cards. I pull a marble out of the bag. I look at the color, I put the marble back in the bag. When I go to draw the second marble, I don't change the denominator, right? Because it's still got the original number of marbles as I had the first time. So those are independent events. Okay? So either they involve two totally separate things, roll a coin, toss a die, independent, or, well, rolling a coin, you could roll coins, I guess. But, tossing a coin and then tossing it again, is that dependent or independent? Independent, right? Because the effect of the first toss has no effect on the other. Rolling a die and then rolling the die again, dependent or independent? Independent. We can make it dependent by saying, rolling a die and getting a 4, and then rolling a die and getting a sum, if you add the two numbers together of 7, that becomes dependent, right? Because I had to get the 4. Okay, if you remember the way we do it, it's the probability of B given A. Okay, so just be able to distinguish between dependent events and independent events, and the formula is... So in words, probability of A and B, so remember, dependent, independent deals with the word and. Mutually exclusive deals with the word or. Or is the union, it's bringing together, and is the intersection. So the formula is just P of A times P of B. And then the one that you're going to get on your formula sheet looks like this. Okay? So those are independent, right? Because you don't have that B given A, right? Given that A has happened, because we don't care if A has happened, because A happening has no effect on B, right? Rolling coins again. Rolling the coin and seeing how it lands has no effect on rolling another coin or the same coin again. Okay, so let's just do 150. No, let's do a couple of examples of this and see what we get. All right, a coin is tossed or rolled. Either way, it's going to land. A coin is tossed and a single six-sided die, a single oh, that's redundant because single and dies are single. Single six-sided die is rolled. Find the probability of getting heads and 3. Okay, so we're going to find the probability of getting heads on the coin and rolling 3 with the die. Now, we could could do a tree diagram, right? But with independent events, I mean, sometimes if there's only a couple things going on, in this case, there's how many outcomes are there here? Coin is tossed, how many outcomes for the coin? 2. Die is rolled, how many outcomes for the die? So how many total outcomes? Fundamental counting principle? 12, right? 12 outcomes. So if we draw a tree diagram, we're going to have 12 outcomes, right? We don't necessarily have to do that. So we would say the probability of head and 3, whoops, only we use this notation. Okay, what's the probability of getting ahead? Depends how much you study. You'll get ahead if you study more. 1/2. What's the probability of rolling a 3? 1 out of 6. What's the probability of a head and a 3? 1 out of 12. Okay, and because we know there's 12 outcomes, right? Only one of those will be head and 3, right? Because you got H1, H2, H3, H4, H5, H6, and T1, T2, T3, T4, T5, and T6, right? That would be the 12 outcomes of tossing a coin and rolling a die. A card is chosen at random. Okay, unless we say otherwise, it's a standard deck of 52 cards, right? A card is chosen at random, replaced, and then a second card is chosen. Okay, so when you see replaced, what do you think? Independent events, right? That I'm just going to go P of A and B, or intersection B is P of A times P of B. There's no dependency. What would make it dependent? What would it say instead? Say not replaced, or something to that effect, right? So replaced, put back, whatever. What's the probability of choosing a jack and then an 8? What is the probability? Okay, so we sit down, we get the formula out. Probability of jack and 8, I just read that as and, right? I'm going to say, but it's intersection 8 is probability of jack. Because it's replaced, then I'm going to use this formula. If it wasn't replaced, then I would write probability of 8 given jack, right? And that would change, the second probability would change. How many jacks are there? Out of? Let's put back, how many 8s are there? Out of? 52, right? In a dependent probability, this would become a 51. It would be 4 out of 52 times 4 out of 51, because we wouldn't have put the jack back. Okay, in this case we have, and this works out to 1 over 169. What's the probability of getting an 8 and then getting a jack? It's the same, right? So really, this is what's the probability of getting one particular card and then another particular card. It could be a jack and then a jack. Okay. If it's independent events, this could be jack and jack. These would be exactly the same, right? Just the probability of getting a particular rank and then getting that rank again. So probability of a jack and then an 8. Remember, the order matters here, right? Probability of an 8 and then a jack is the same. So if we did, so what about probability of 8? So it'd be the probability of an 8 times the probability of a jack, which is 4 out of 52 times 4 out of 52, or 1 out of 169. But here's the ultimate question. I do this situation. A card is chosen randomly, replaced. The second card is chosen. What's the probability that the two cards I got were jack and 8? But not necessarily in that order, just so that I got a jack and an 8. or an 8 and a jack. What would that probability be? You can do it. You got all the numbers you need. They're all there. 2 out of 169, right? Because then we're saying, well, remember, each of these is a particular order. It had to be a jack followed by an 8. New text sound. This one was an 8 followed by a jack. If I want to just know what's the probability that in the draws I ended up with a jack as one of the cards and an 8 of the other, as the other card, so I'm implying the order that I drew them in doesn't matter, then I would add these two probabilities together. What it would look like is really this. It would look like the probability of jack and 8 or, so it would look like this, right? It's the probability of getting a jack and an 8 or the probability of getting an 8 and a jack. Okay? And then you would simply take these and say, well, that's 1 out of 169, or translates into a plus 1 out of 169. So 2 out of 169. So really, a lot of this is just very carefully reading the question, right, and interpreting. Does it have to be a jack and then an 8? That's only 1 out of 169. Or is it, I've got a jack and an 8, and it doesn't matter which one I got? Then for independent events, you really just double it. Okay? Because the independent events, they're going to be the same probabilities. You just have to multiply by 2, right? Or add the 2 together. But either way, same difference. If they're dependent probabilities, then you have to work each one out because they may in fact be different, right? Especially if it was jack followed by jack or something. Okay, let's go to a jar of marbles. A jar of marbles contains 3 red, 5 green, 2 blue, 3 red, 5 green, 2 blue, and 6 yellow marbles. A marble is chosen at random from the jar. Jar, period. After replacing it, a second marble is chosen. After replacing a second marble. What is the probability of choosing a green and then a yellow? Actually, you know what? Let's do 3 of these. So, A. What is the probability of choosing green, then yellow? Okay, so let's just work that one out first. Okay, dependent or independent? They're independent, right? How do we know? Because we're replacing it, right? So we see the word replacing. So remember, if it's the same thing that's happening, right? Draw a card, draw a card, draw a marble, that could be dependent, it could be independent. So we need further information. If it's draw a card, draw a marble, those are obviously independent because they're two totally separate things, right? But if the same thing is happening, draw marble, draw marble. Okay, so what's the probability of choosing green? What's the probability of choosing green? So how many greens are there? 5. How many marbles are there? 16. So it's 5 out of 16. Okay, so green then yellow. So let's write out a little form, right? So probability of green and then yellow is the probability of green times probability of yellow. If this was independent or dependent, we would go times the probability of yellow given green, right? We know our denominator would change because we'd have fewer marbles. But Not the case. So 5 out of 16. And the probability of yellow? 6 out of 16. And that's equal to, what, 30 out of 256, or 15 out of 128. Yes. Somebody may want to check that.
It's the 15.
That's the reduced thing, right? Now, sometimes your book is giving you, it's first printing of the book, and, they might give you an unreduced fraction. It should be reduced. And actually, in the answer key that I have, they've reduced those. So when you're seeing stuff like 92 out of 182 or something, they have reduced all of those. Okay, and generally it should be a reduced fraction. What? Who now? Okay, so you work out yellow then green. Okay, so part B, do yellow then green. What is the probability of choosing yellow then green? Hey Dante, if you're gonna sleep, just go down to the guidance thingy. Okay, now it's the same, right? Because you're just taking the exact two numbers, but you're multiplying them in a different order, right? So probability of yellow is 6 out of 16, and green 5 out of 16, and that's 15 out of 128. So what's the question for part C? C. Come on. What's the probability of having drawn a yellow and a green? Okay. Without regard to order, right? So what's the probability? So after the draws, so after completing two draws, what is the probability the marbles were yellow and green? So you should extend the page. So what is it? 30 out of 4? 15 out of 64. Okay, so how do we get that? Add them up, right? Or just double it. Okay. Now, if it was dependent events, we wouldn't just double it because they could actually be different probabilities, right? So we would add them together. But we're just going to add them together. So really, you need to be able to look at the wording and say, and usually, it should be yellow then green, and that gives you an order, right? The first one is yellow, the second one is green. Green then yellow. Okay. First one is green, second one is yellow. What's probably having a green and a yellow? Doesn't look like the order matters there. So I'm going to double up, right? So it's 15. Well, okay. More formally, it looks like this. So it's the probability of green and yellow, or yellow and green. We've already worked out those individual probabilities. 15 out of 128. Union corresponds to plus 15 out of 128. 30 out of 128, or 15 out of 64. Okay, so just be aware of that. It's just a twist in the question, right? It's just a little. Okay. Now, we know that events can be dependent or independent. How can we classify them if we know the probabilities? So, here's the question. Determine what you won't have to do. So everything you write from now on, there's no written. Okay, so probability test, all multiple choice. Field test, multiple numeric. Final exam, multiple numeric. Quest A+, multiple numeric. You're done. No more writing. You don't have to show any work. But on the probability test, show your work. Okay, please show what you're doing, because if you get it wrong, you want to know why. Okay. Oh, should I have used that formula, or did I need to add them together? So if you write down what formula you use, because it's more important you learn from your mistakes. If you're going to make any mistakes, you want to learn from that prior to the field test, and then prior to the exam. Okay, determine if events A and B are independent events. And we're going to do two. So part A, given that the probability of event A, the probability of event A intersect B is 0.2. Probability of A is 0.6. And the probability of B is 0.4. You're going to get a question like this. I'm 90% sure you're going to see something like this on the final. Determinative events, they won't be determined if they're independent events, but it'll be something along that line, right? Like figuring out if these are independent or dependent events. So given that probability of A and B, or intersect B, is 0.2, the probability of A is 0.6, the probability of B is 0.4, are they independent? I see one, I see two. How do you know that they aren't independent? So if they were independent, this is true, right? And what do we know? Well, we know the probability of A is 0.6, and we know that 0.4, and you multiply those two together, what do you get? And how does that compare to that? Not the same. So they are not independent, which means they must be dependent. Okay? But it's not asking us if they are dependent, right? It's just saying, are they independent? And we say, no. Okay? So not independent. How do we know? Because if they were, that formula has to hold, and it doesn't, right? It's not true. Okay, given that if I want this to be true, what's P of B going to be? If I want these to be independent events. 0.8, right? 0.8. Okay, so there's the question. What do you do? Well, if they're independent events, you say, if they're independent, then this holds. At 0.7 times 0.8, which is 0.56. That matches. So they are independent. Right? So using the formulas and some information, you can calculate whether events are independent or not independent. Remember, dependent, independent, go with the word and. Mutually exclusive works with the word or. Usually mutually exclusive is a single thing that happened, right? I drew a card with one event, and I want to know if it was black or a face card. There are 3 children in the Smith family. Determine the probability that 2 of them are boys. Okay, if you have a child, what's the probability that it's a boy? 50%. Now, you know, there's an article in the paper the other day about strange names that parents have given their children, like Thunderbolt and Rainy Day. assuming Thunderbolt's a boy or Andy Day's probably a girl. But anyways, as part of that though, they said there were this many boys, this many girls born last year. It worked out to be 51.5% boys and 100 minus 51.5% girls. So there was a slight, right, because males tend to do stupid stuff and kill them. That's my theory anyways, kill themselves off. So nature accommodates for that by making a few more boys to make up for the fact that they won't be around that long. So one way that we could do this is through a tree diagram. Okay? So we'll say first child, second, third. First child could be a boy or a girl, and the associated probabilities are 0.5 and 0.5. Second child, if the first child's a boy, it could be a boy or a girl with the associated probabilities. And the third child, and if it was a girl as the second child, we get the third child. And if a girl was the first child, we could have a boy or a girl. And so on. And each of these probabilities are all the same, right? And when you're doing a tree diagram, they don't necessarily have to be the same. Right? I mean, maybe we're going to use 0.515 for the boys and whatever the other one would be, 0.485 for the girls. And that would change things. But to make life easy here, we're just going to go with 0.5s. So the probability of having, and then what we do is we trace out the tree, boy, boy, boy. We multiply, right? Because it's an and probability. It's a boy and a boy and a boy, right? It's not boy or boy or boy, right? We're not going along saying or. It's boy and boy and boy. 0.5 times 0.5 times 0.5, which is 0.125. And the next one is boy, boy, girl, also 0.125. Boy, girl, boy, also 0.125. Boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy. And girl, girl. Now, each of these outcomes are unique, right? I mean, having boy, boy, girl doesn't imply. Boy, boy, girl says the youngest child is a girl. Girl, boy, boy says the oldest child is a girl. But all we care about with the Smith family is not necessarily who's the oldest, the youngest. We just want to know what's the probability that two of the children are boys. So what is the probability that two of the children are boys? Well, yeah, exactly two. Yeah. Did I? If I didn't say that, then I should have said. Term probability that two of them, so that exactly. Good question, all right? Because yeah, we should. Is it exactly two? Is it at least two? So the probability of two boys and a girl is the sum of these individual probabilities, right? Where the girl is the eldest, the middle, or the youngest. 0.375. 37.5%. 375 out of 1,000. That reduces to something 3 out of 8. Okay. So remember, probabilities can be expressed three ways, right? As a decimal, as a percent, so decimal, percent, or fraction. And you're going to see them all on the test, right? Sometimes it'll be percents, but you'll know before you do the question, right? When you look at the answers and you say, oh, they're all decimals, I'm just going to leave my answer as a decimal. Oh, the answers are all in combinatorics notation. I'm not going to work it out then. I'm going to leave my answer in combinatorics or see which one of these matches the situation. Okay. Move down. Let's just go to a new page. Okay, say so, Annie and Bobby are playing a coin and die game, right? So it involves a coin and a die. Each turn consists of rolling a regular six-sided die and tossing a coin. Rolling a regular six-sided die and tossing a coin. Determine the probability of rolling a 2 or tossing tails. But not both. Okay, so it's probably rolling a 2 or tossing tails, but not doing both. So, one way to solve this, again, is with a tree diagram. So let's do it this way. 2. Not 2. What's the 2 with the 2 prime? What's that mean? Yeah, not a 2, right? So what's the probability of rolling a 2? What goes on this branch? What's the probability of not rolling a 2? 5, 6, right? So we've got a tree diagram, but this time we have different probabilities in the branches, right? 1/6 of rolling a 2. Then we want to toss a coin, right? Tossing a coin, you get heads or tails. What's the probability of getting heads? Probability of getting tails. If you don't get a 2, what's the probability of getting heads? Well, okay, those are just halves, right? So following the branch, getting a 2 and heads would be 1 out of 12, right? Getting a 2 and tails would be 1 out of 12. Getting a 2, not a 2, and heads, what's that probability? And getting not a 2 and tails, what must those add up to? 12 out of 12, right? If they don't add up to 12 out of 12, then you've made a mistake. Okay? Because this has to be every possibility, right? And it is every possibility. Because you either get a 2 or you don't. You either get a head or a tail. There's no coins landing on their sides. There's no dice sitting, hovering on an edge. Okay. So, what did we want? We wanted the probability of rolling a 2 or tossing a tail, but not both. So, which events should I circle? All right, so let's ask this. Does this involve rolling a 2 or getting a tail? Yeah, because you got the 2. Does this involve a 2 and a tail? Yeah, but it also has both, right? So we don't want that. Does this involve getting a 2 or a tail? No. Does this involve getting a 2 or a tail? it's not twos, but it is tails. Okay, so what's the probability we're looking for? 6 out of 12 or 1 out of 2, right? 6 out of 12 or 1/2. So the total. So 6 out of 12, 1/2, 0.5, 50%, right? Can be expressed in a lot of different ways. All right, last one. Is that your last example? And so tomorrow review, Thursday the test. The Student Activity Council is having a raffle. And they have sold 200 tickets. Period. There will be 2 draws. What's the piece of information you now need to know? No, assuming there's one ticket in the draw. Right? Do they replace it? Right? What do you think? Well, this section is on independent events, so they're probably going to replace it, right? Okay. But, tomorrow when you're doing a review and stuff, then it's, you have to figure out, is it independent or dependent? So it'll be 2 draws. After the first draw, the ticket is replaced. Or the ticket gets put back, right? Anything that implies replacement, so it gets put back. So we'll say, I purchased 4 tickets. Determine the probability to the nearest tenth of a percent. Okay, so we gotta figure out what the probability is, change it into percent, round it to how many decimals? Determine the probability nearest 10th of a percent that he will win at least 1 prize. So how many prizes could I win if I win at least 1? 1 or 2, right? Okay. Best way to handle this, and I think really the best way to handle a lot of these probabilities, is to draw yourself a tree diagram, right? And maybe you get more than you need by drawing the tree diagram, but at least you've got everything you need, and you don't leave something out. Because the problem with not doing tree diagrams is maybe you leave out one of the possibilities that you should be including. Okay, draw the tree diagram. At worst, you've worked out more than you need. You don't necessarily have to. You could just say, hey, I need this branch and this branch, right? These are both where, remember yesterday with the goalkeeper? I only need these branches where I end up playing the goalkeeper, right? Where it says yes. So I only need to calculate those branches. I don't need to calculate all 4. But we draw out all 4, and then we say, all right, we need to calculate this one and this one. So now let's do that, right? You can be a little more efficient in your calculations. Okay, so you could win first prize or not win first prize. What are my chances of winning first prize? How many tickets did I buy? 4 out of 200. What's the chances of not winning first prize? 196, right? Out of 200. Okay, if I win first prize, I could win second prize or not win second prize. What are my chances of winning second prize, given that I won first prize? So I won first prize, what are my chances of winning second prize? Same. How would this change? If it was dependent, this would be 3 out of 199, right? If they didn't put my ticket back, this would change to 3 out of 199. But we did put the ticket back, so it's 4 out of 200. What's the probability I don't win second prize? 196 out of 200. If this were dependent, this would be 4 out of 199, right? Because I still would have 4, and and this would be 3 out of 199. That's all we got to do, right? It's just first, second prize. So second prize, not second prize. How do these compare to these? Exactly the same, right? 4 out of 200 and 196 out of 200. So what we have here is, this will be the probability of first and second, right, which is 4 out of 200, which is 1 out of 50 times 1 out of 50, or 1 out of 2,500. This would be the probability of first and not second. Okay. Do we need that? Is that part of what we need? It is, right? Because I need to win at least, so we need this, right? Because that would be me winning both prizes. This is me winning first prize but not winning second, but at least one prize. That's part of it. Okay? So it's 1 out of 50 times, what is 196 out of 49 out of 50? Okay, which is 49 out of 2,500. This is the probability of not winning first prize but winning second prize. Do I need this probability?
Yes.
Yes. What's the one I don't need? I don't need the last one, right? I don't need to work that out. Now wait a second. Do I need to work that out? Because what am I going to end up doing here, right? I'm going to end up figuring out 3 probabilities and then having to do what? Add them together. But what do all these probabilities add up to? 1. I can figure this probability out and do what with it? Subtract it from 1 and end up with the probability that I want. So instead of working all these out, let's just work out this one probability where I don't win any prizes. And then subtract that from 1, because what's left? Right? The complement of not winning any prizes is winning at least one prize. So in retrospect, it's better to work out this one probability, 49 out of 50 times 49 out of 50, which is whatever that works out to, and then subtract that from 1. So go 1 minus 49 out of 50 times 49 out of 50, and what do we get if we do that? Borrow your calculator. 1 minus 50. I get 0.0396. 0.0396. So to the nearest tenth of a percent, what is it? So that's just taking that, converting directly to percent to the nearest tenth of a percent, 4.0%. Okay? And that saves a little bit of work from, hey, let's work out all 3 of these and then add them all together, potentially making a mistake along the way or something. Instead, wait a sec. This is the only thing we don't want. These have to all add up to 1. 1 minus that number gives me the number that I want. This concludes your Math 30-2 course.